Hello. Good evening, everyone. Today I will explain about how time series prediction helps wind power integration. So time series will be related to the machine learning, and then wind power integration will be related to renewable energy. It's a little bit about myself. My name is Thursy Satriani. I'm a machine learning engineer at Cloud Singapore and has a master's degree in EECS. My research focus actually in AI in renewable energy. And I joined one of a cool event from Google, which is Women Developer Academy, which is help us in terms of skill, resources, and support us to become a speaker. And today I give it a shot. And then I will start it with renewable energy, so information related to renewable energy, and after that we go to the machine learning. So renewable energy is the energy that is collected from renewable resources. This is actually the current condition with a total 25,000 terawatt hour. This is what we need in a year, and 38% is generated by coal, which is fossil fuel. And then only 6.6% is generated from the renewable energy, which is solar, wind, geothermal, and tidal. And then why actually renewable energy start to become an option? Because first, it's clean. So compared to the fossil fuel, it's cleaner. The CO2 emission is increased by 2.5% itself only due to fossil fuel generation. And then it's safe. If you compare it with nuclear energy is actually a very optimized way to generate energy, but it has like radioactive waste. And if the nuclear plant is located in the area that has potential to have an earthquake, it's very dangerous. That's why people start to move to renewable energy. And it also modular. Yeah, you can put solar panel on top of your rooftop and it will working. And then there are two options actually in the wind, in the renewable energy, which is very popular, wind and solar. For the wind itself, one wind turbine able to power 250 homes, and then one wind turbine itself normally generated around 4 megawatt or 6 megawatts. So like one wind turbine able to power around 1,000 until 1,500 houses. And then for the solar, actually it's very easy to install. That's why it's become an option. And then in this case, I will explain about wind power generation because it's one of the research I did when I took my master degree. This is a wind turbine. It started with a kinetic, which is the wind speed. We'll talk about wind speed later on. It starts to turn on the blade, and then after that, the shaft, and then it generate the electricity. So wind speed is vary all the time, and also it has specific characteristic for a season. Normally in summer, you will have less wind speed. And then in the winter, you will have like high wind speed. This makes sense actually because the different of temperature, different pressure, you will have different movement of the wind. And then also I got the wind speed because we want to predict wind power. We need to change the wind speed into wind power, and then you need this kind of information. This information is actually power curve. You need to pay attention this pink dot over here, pink curve over here. It started by 2 meter per second. That actually it start to turn on and generate power. After it's get into 15 meter per second, it will generate 4.2 megawatt, which is the maximum. And then until it's 25 meter per second, you will have turbulence. So cut off. You will no longer generated any power. So what I said earlier, we need to dealing with uncertainty because of wind power. We don't know exactly how much wind speed, and then we don't know how much wind power, something like that will generate. So this kind of difficulty is lead us to something called negative pricing. So negative pricing is instead of you getting paid because someone uses your product, you paid someone to use your product. It happens because sometimes you generate too much electricity, and then there are two options: store it in the battery or release it to the grid. Store it in the battery sounds really good option, but battery is very expensive, the mechanism to store it and release it back very complicated. That's why people just release it to the grid so people can use for free, or even they ask someone to use it. In this case, for the machine learning, we will use different, there are 4 different time scale here, but I just use medium term, which is you're trying to predict several hours ahead until 1 week ahead. In this case, I use 24-hour ahead. So you're able to know what power generated tomorrow, at least, yeah. And then for the input, I will use, this is wind power, actually, wind power data. There are 7 different locations. So I use CNN in this case to process this all. So this is the target is in Taiwan. So Taiwan government trying to build up wind power in offshore. So in the middle of the sea, they put wind turbine here. And then they did some research to eliminate the uncertainty, something like that. So this is the data. And then the input output pair is discussing how I calculate the R square from 1 hour ahead until 24-hour ahead. And then this is the method. This is 1D CNN. It started with the 78 hour as a window size. It will be moving along different timing. And then after that, we'll also have in here, this is the filter actually. And then you will have convolution, subsampling, another filter, convolution process, subsampling. You concatenate it together, flatten it out, concat them together, and after that, fit it in a fully connected, and then you got the output. 2D is the same, but instead of using one-dimensional data, if I use Fuhai wind farm dataset to predict Fuhai wind farm dataset, but in this case, I use 7 different location information to predict the Fuhai dataset. That's why it can become 2D and then can be processed using 2D CNN. And after that, this is the filter, and then convolution, subsampling, flatten, and after that concat, hidden FCN output. So it's similar, just it's 2D data. For 1D CNN result, this is the result. So this is the R square of the average R square. This is in the different season, because I separate them to winter, spring, summer, and autumn. And then this is the variance that generate from this R square. SNR is signal to noise ratio. So basically it's just logarithmic ratio between the average and then the variance. And you got the robustness result. And then you can see that this is the red one is the prediction. And then the blue one is actual. It's almost overlapping each other. So I think it's pretty good. 2D CNN, I use summer data set. So this is the result. It's higher compared the 1D CNN because it got more data, more parameter. So this is the comparison actually between 1D and 2D CNN result. So this is the one that we did in the research. It's around 0.91 R square. And then the optimal design is in 2D is 0.93. And then the SNR are also showing a higher number. Okay, come to the conclusion. Actually, the 1D and 2D CNN that we use is actually have higher R square, low variances, and high SNR. But 1D CNN and 2D CNN optimal design outperform the existing method in terms of SNR. And then 2D CNN has higher SNR compared to 1D CNN because the utilization of 7 different locations increase the R square and reduce the error rate. So, okay, that's it. Thank you.
So someone asked, can you explain more about the technologies you use to build the CNNs?
So to build a CNN, I use a library that are available in TensorFlow. So I use TensorFlow and then Keras on top of it, and then designing what kind of a layer I want, how many of it, and then design how many fully connected I want, something like that.
How much computing power do you think is needed for an analysis you have done? And how long does it take to get an accurate prediction?
Because it's research, it take a long time, I think, to study about this. It take like a year to knowing what kind of thing I should use and why I use this method. But for the hardware, I use NVIDIA. I use NVIDIA 2080 GTX. So it's pretty brand new at the time. I don't know. I think it's still new. So it's kind of fast. I think it's spent 3 minutes only to run 1000 iteration CNN for CNN, but for LSTM it's still very slow. That's why LSTM I think took hours. That's why.
3 minutes versus hours.
Yeah, because
Wow.
a different method.
How do you turning parameters?
Tuning.
Yeah,
Tuning
maybe it's a
parameter.
typo. Yeah.
Oh, yeah. I think in this case, actually, I use the method called Taguchi method. Normally, we just use ad hoc method, like we try. If it's bad, we increase it. If it's still bad, we lower it, something like that. But in this case, I use Taguchi method. It's a method that normally used by civil engineering when they're trying to design something. So you determine the range, and then you only try like maybe 18 different possibility out of it. After that, you calculate the SNR, and then there's other method that you can find your optimal design. Actually, my optimal design is came from that one. Yeah, it's suggested by the Taguchi method. Yeah, maybe you can check this paper over here because it's actually submitted and then published under this title. They had spatial temporal wind speed forecasting using robust design-based deep learning.
The one at the bottom left of your slide.
Yeah, you can find it in the Elsevier Energy Journal.